All right, well, that's all nice to look at. Is there another way to maybe try to actually show an example of how this might work, and how is this useful? Well, this can be shown with the convolution. The definition of convolution is the following. The function f of t convolved, so we use that little star operator, with the function g of t is equal to the integral from 0 to t of f of tau times g of t minus tau d tau. And one way to think of this is that it's an operation that when I take this integral, I get another function of time, which describes how the first function modifies the second function over time. Because notice this, we're integrating over this variable tau, this dummy variable, and so this is where g of t minus tau is being evaluated at some offset over all possible times. So it's because this integrates out to t. So it's a little bit abstract to think about, but let me show you an example. Let's say we have the relatively simple second order differential equation x double dot plus omega n squared x is equal to f of t, and x evaluated at 0 is 0, and x dot of 0 evaluated at 0 is 0. Then we could go ahead and take the Laplace of both sides of this thing, and that's equal to the Laplace of f of t. And we know we can take a second derivative, so I get s squared. I evaluate all the initial conditions are 0. So I would get s squared plus omega n squared all times x of s is equal to f of s. So then I have x of s is equal to f of s times 1 over s squared plus omega n squared. Notice this is equal to f of s times g of s, where g of s is just 1 over s squared plus omega n squared. But there's the convolution theorem in Laplace says that the Laplace of the convolution of two functions in time is equal to the product of the Laplace transforms, where now this is regular multiplication. So that means that these two, right, that's f of s and g of s, there's f of s and g of s. So this thing over here, if I were to go back in time, has to be equal to the convolution. And another way to make use of this is to take the inverse of the whole thing. So if in other words, I take the inverse Laplace of the Laplace of the convolution of the two functions in time, that has to just be equal to the convolution in time, which has to be equal to the inverse Laplace of f of s times g of s. But notice over here, this is f of s times g of s, where g of s is the 1 over s squared plus omega n squared. That has to be equal to x of s. So this has to be equal to the inverse of x of s, which by definition is just x of t. So how can we use this result for x of t being the convolution of the two functions f of t and g of t to solve for x of t? So first, let's let f of t be the impulse function, and according to the Laplace tables in the book, the Laplace of delta of t is just 1. So that means that x of t is equal to the convolution of delta of t and g of t, which we now know is, g of t, And from the tables in the book, g of t, if g of s is that, then g of t has to be sine of omega n t over omega n. So I can go ahead and plug all that into the convolution integral. And so I need to take the integral from 0 to infinity of g of t, which is now sine of omega n times t over omega n, times delta of t minus tau, d tau. But remember, the delta function, the impulse function here, is only active when t is equal, when I add 0, so t minus tau equals 0. So it's only active when tau equals 0. So this effectively is just like 1 and then 0 everywhere else, except for when tau equals 0. So what I end up with is just sine of omega n of t over omega n. Well, if you notice, this is the homogeneous response with 0 initial conditions for this harmonic oscillator up here, right? You're going to get sines and at the natural frequency. Well, that's interesting, and we'll have to explore that a little more. But what about when, say, let g of t equal the cosine of omega n of times t? Well, we can go ahead and throw everything into the convolution integral, but let me just note that this is equivalent to saying that we have x double dot plus omega n squared x is equal to cosine of omega n of t. So I have a harmonic oscillator that has a forced input, or what I know is that I'm going to get a particular solution here, right? I've got the homogeneous solution with 0 initial conditions. Now, what's the particular solution? Well, according to the convolution integral, then x of t is just the integral from 0 to infinity of sine of omega n t over omega n times the cosine of omega n times t minus tau, d tau. And we can do this integral. We have to do integration by parts and separate stuff out and blah, blah, blah. But if you go through and look at it, what you end up with is 1 over 2 omega n t times the sine of omega n of t. So this is the particular solution to this differential equation. So we can verify that that is indeed the right solution using the dsolve command. And one way to do that is to just, again, plug everything in, type it in, and set the initial conditions. And we get kind of this long answer because it's got all these exponentials. So we use the simple command, and then we use the pretty command. And in fact, we find that the solution is t times sine t omega n over 2 omega n. So the convolution actually gives us a way to determine the time response of the system with some non-zero input. So it gives us the particular solution, assuming that the homogeneous response of the system is evaluated when the initial conditions are 0. So what we need to do is find a way to combine these two things together, and the transfer function, along with some other theorems, are going to allow us to do that.